Hey everyone, welcome back to Calculus 1. This will be lecture 6 of the course, and in this section we're going to begin our study of derivatives and differentiation. Let's go ahead and jump into it. So we'll call this section 2.1 Introduction to Derivatives, and this will be part A of that lecture. Probably the most natural way to start any discussion of differentiation and derivatives would be by introducing the tangent line problem. And so to start with, what is a tangent line? Well, the most intuitive way to start that discussion is by thinking of a circle. So for a circle, if we think of a circle, I've got one drawn here. We think of a circle, that circle is going to have a radius. And if we think of that radius as being what we would call the radial line, so some line extending from the center of the circle to the edge. If we draw another line that's perpendicular to that radial line and touching one point of the edge of the circle, now that's hard to do in practice, but theoretically speaking, you could imagine it. That line is called a tangent or a tangent line. Okay. And so in the case of the circle where the curvature is constant, we can just think of it as a line that is perpendicular to the radius of the circle. Okay. And that line, this orange line here, intersects the circle, theoretically speaking, at exactly one point, and we've marked that as P. Now, of course, in practice, you can't say that, or you can't draw that, but you can imagine theoretically, conceptually, in an abstract way, a line touching the circle at one point. Okay? And that's what we mean by a tangent line. So the idea of a tangent line becomes a little more challenging with a general curve, but if you just keep in your mind the idea of the line touching the curve at one point, and so the orientation of the line has to be kind of guided by that. That's sort of the general principle when thinking about a tangent line, at least visually. All right, so I've got some examples here. So the first example, we've got this kind of curved line here that comes up, and we've drawn a tangent to that curve at the point P again, right? And so you can imagine this intersecting that curve and just touching it at one particular point. Similarly, here in the center, we've got another line kind of descending this time, and the tangent line that we've drawn in intersects a point P on this line, right? And so you can see it's just, theoretically speaking, just touching the curve at that one point. Okay, now don't be bothered by the fact that it's going to intersect the line elsewhere. In the neighborhood of this point P, it touches that line at precisely one point. And then another line drawn here, another curve here with a tangent line again drawn at a point P. Okay, so the key idea here is, while it is, of course, impossible to draw, you can imagine these lines being thin enough and precise enough to actually touch the curves at one point. So you have to kind of go into your geometry mind space and imagine such things, right? You can't draw it, but you can imagine that reality. And so the idea that this line here, for example, touches this underlying curve at one point is going to inform the orientation of this line. Namely, the line is going to be tilted in this direction rather than like this, right? The idea that it touches one point kind of helps align the point with the curve. It just grazes one point of the line. Okay. All right. So that's what we mean by a tangent line. And so the idea with a tangent line problem is, how do we identify a tangent line? In the case of a circle, we have sort of a formulaic process that we can apply, namely find a radial line and identify a line perpendicular. So we can do that. But in the case of a general curve, like the ones that I've drawn here, how do we go about actually identifying the tangent line at any particular point? So that is the problem. And so one way to approach the derivative is to think about how we might go about finding the slope of the line that is tangent to a given point. Because if we can identify the slope of the line, we can identify that it goes through a particular point, then we have the line, right? And so let's start with it. Let's kind of move the discussion into the area of slope. So let's recall what we do for slope. So with slope, we typically use the idea of m as the notation, and then we use the idea of the rise and run, right? So m equals y2 minus y1, so the change in y, divided by x2 minus x1, the change in x. We refer to that as the rise over the run in algebra. And then a notation that we'll use a lot in calculus that is sometimes introduced in algebra is the notation of delta y over delta x. And that delta just means change, right? So this is the change in y over the change in x. Okay, and so like a quick example, let's say I've got a straight line in the plane that intersects the points 1, 2, and 8, 6. The slope of this line can be easily found by using the formula m equals y2 minus y1 over x2 minus x1. I can plug those values in, so I get 6 minus 2 divided by 8 minus 1, and I see that the slope of this line here is 4/7. Okay, so this is algebra stuff. We've all seen this before. This isn't the new stuff. But what we want to do is we want to kind of remind ourselves of how slope works, and then kind of we want to start thinking about this notation with the delta x and the delta y. Okay, the idea of a change in y divided by a change in x. Okay, and so remember, delta x is the change in x, so it's kind of like the horizontal leg of a right triangle, and delta y is the vertical leg of the right triangle. So we've got a right triangle here, right? Okay, and so letting delta x denote the change in x and delta y the change in y, the slope of an arbitrary secant line can be calculated using this formula. Okay, so let's remind ourselves what a secant line is. A secant line is just a straight line that intersects a curve, right? And so if it intersects a curve and it's not a tangent line, then it must intersect the curve at more than one point. And so we've drawn one in here. I've got the function here in red. And then on top of that, I've laid in an arbitrary secant line here. Okay. And so the secant line intersects the curve here, and it intersects the curve here as well. Okay, 2 points. Okay, and that's what we mean by a secant line. It's like a tangent line, except that it intersects the curve at more than 1 point. Okay. And so I've also laid in some axis labels here. So let's look at what I've got here. So for this point down here, that is called C on the x-axis. And so therefore, when I evaluate it, I get f of c, right? And so the point itself can be thought of as c comma f of c. That's the ordered pair for that point right there. And similarly over here for this other point on the x-axis, I've got kind of a funny label. This will be new to you if you've not seen calculus before. This is not something we would normally do like in algebra. But basically what I've done is I've labeled this spot on the x-axis c plus delta x. So the idea is between c and this new spot on the x-axis is a distance of delta x. Right, and so this is c, then this is c plus this additional distance, delta x. Okay, so kind of a weird way to notate it, but as you'll see in a moment, there's a very good reason to do this. Right, and so then up here, the ordered pair for this line would be c plus delta x on the x-axis, so that's just this guy, c plus delta x. And then, of course, when we evaluate the function, we're going to plug c plus delta x into the function. And so that gets us f of c plus delta x. Okay. And so this is I know, like, to the noob, this seems very like cumbersome and awful, but it'll all become clear in a moment. So just bear with me. Just understand that all we're doing here with this c plus delta x is we're saying, well, here's c, and there's some additional distance called delta x that we are to the right of c. And so this point could be called c plus delta x. Okay. All right, so now let's think about our slope formula up here. So m is equal to the rise over the run, right? Which we know from algebra. We can think of that as y2 minus y1 over x2 minus x1. Okay, and then in our newer notation, that's delta y over delta x. So the change in y, i.e. the rise, divided by delta x, the change in x, i.e. the run. Okay, now if I take what I've drawn over here and I plug it into this, this is what I get, right? So the change in y is this piece, right? So that's the delta y. I've noted that here on the actual picture, right? So the delta y is going to be f of c plus delta x. That's the point on top, minus f of c. So that's the lower section, the lower point. So that's the delta y. That's the change in y. And then what's on the bottom? Well, that's the change in x. So that's going to be c plus delta x minus c, right? And that's what you see here. Okay. And then, of course, c plus delta x minus c, well, the c minus c is just 0, so that denominator is really just delta x. Okay? All right, so that is the slope in terms of this schematic here. Very important, right? Get comfortable with this picture. This will having comfort with this picture and with this formulation of the slope is going to make the idea of the derivative much more straightforward. Now, when you look at this thing here, specifically this thing here, you may recognize this if you've taken pre-calculus. This is something that comes up in pre-calculus, and it just kind of comes out of nowhere. You do a few things with it, and then it disappears. This is what they call the difference quotient in pre-calculus. So f of c plus delta x minus f of c divided by delta x. And again, if you took pre-calculus, you might remember seeing this, but you might not remember seeing it. You definitely would have come across it in pre-calculus, but its value and import was probably missing, probably was not adequately conveyed to you, which is the case with pre-calculus usually. But what you probably did was plug some values into this, evaluate the difference quotient for a handful of functions, and then just probably walked away from it. Well, here's where the difference quotient comes into usefulness. So what I want you to do next is I want you to keep this picture in mind, right? And the idea of this secant line. Now, I could draw any number of secant lines, right? I could draw a whole bunch of them. I could draw infinitely many, right? As wherever I want, just intersecting this point. So what I want you to do is I want you to imagine the 2 points on the secant line getting closer to one another, right? And specifically, I'm going to fix this lower point. I'm going to leave that one fixed, but I'm going to move the top one ever closer, right? I'm going to kind of bring it closer to the bottom one. Okay? And all the while I'm doing that, the secant line is going to change, right? It goes from being this dark green line to being this blue line, to being this light green line, and then this purple line, and then this gray line. And it's going to continue to go through these changes as I move the second point of intersection closer and closer to this first point of intersection. Okay, so the 2 points are going to get closer and closer to one another until you can imagine what happens in the end, right? Eventually, they're going to be arbitrarily close. They'll be almost on top of each other, right? So you're going to have the secant line 1, secant line 2, secant line 3, secant line 4. They're just going to get, and they're all going to be driven by this point here, and then the successive series of points that you get as you move these points closer. And you can think of those points as getting closer and closer, not just on the graph, but really in the x-axis, right? So C1 is over here, and that's what gives you secant line 1. C2 is what gives you secant line 2, right? C3 gives you secant line 3. C4 gives you the purple, and then C5 gives you this one. And I could continue getting closer and closer to P till I'm arbitrarily close. I'm right up on top of it almost, okay? Now, eventually, as I iterate through all of these points and I get closer and closer, we'll find ourselves in a situation where the secant line intersects 2 points that are infinitely close to one another, right? So I put that in air quotes because it's careful with the way you think about it. But the idea is that they're so close you can't tell if they look like they're right on top of each other. They're infinitely close, air quotes again. Okay, and when that happens, the secant line suddenly becomes a tangent line. Okay, so once those 2 points that the secant line is based on are infinitely close to one another, your secant line turns into a tangent line. Okay, and it's going to be a tangent line specifically at the point P. Okay, so that's kind of the setup for the derivative. If I want to know what the tangent line is at a point P, then the way I get to it is I have to go through this sequence of secant lines. And how do I go through a sequence of secant lines? Well, what I do is I let my second point get closer and closer to my fixed point. Okay, and I do that just basically by moving my second points ever closer to P, right? Just kind of shrinking down the distance between them. Okay, so you can clearly see that between P and C1, they're going to have some delta X. Okay, and between P and C2, you're going to have another delta X, right? And those delta X's are going to get smaller as I move closer and closer to P. Okay, so another way to think about these C1s is that C1 is basically P plus a delta X. C2 is going to be P plus a different delta X. C3 is going to be P plus yet a different delta X. And now these delta X's are all getting smaller, aren't they? Right, so delta X1 would be bigger than delta X2, which would be bigger than delta X3. And this just goes on and on until delta X is so tiny that it looks like C and P plus delta X are the same thing. Okay, so that's the intuition behind the derivative, right? The idea of taking a series of secant lines and getting that series of secant lines by shrinking the delta X between P and these different points on the x-axis. Okay, so that's the intuition. Let's look at the definition of the derivative now. Okay, so here's the definition. If f is defined on an open interval containing c, right? And if the limit, now this is going to be some complicated, this is going to be a complicated expression at first, but it's actually pretty straightforward. So take a moment to really look at this, write it down, let's talk it through. The limit as delta x goes to 0 of delta y divided by delta x is equal to, right, the limit as delta x goes to 0. Now, delta y is what? Well, delta y is just f of c plus delta x minus f of c, right? The change in y, that's all that top is. And the bottom is just the change in x, right? So we saw before that this is just the slope of a secant line, isn't it? Right, so we call it m. But so what is the limit doing then? So if I've got the slope of a secant line, what is this limit telling me? Well, the limit, what's happening here is the limit. This is the limit as delta x goes to 0, which basically means that c plus delta x is becoming arbitrarily close to just c, right? So this is what was happening in this picture here, right? So your delta x is shrinking up, and as your delta x shrinks up, your value on the x-axis named c gets ever closer to p. Okay, so if f is defined on an open interval containing c, and if the limit is delta x goes to 0 of f of c plus delta x minus f of c over delta x exists, if that limit exists, then the line passing through the point c f of c with slope m is the tangent line to the graph of f at that same point. Okay, and it is also called the slope of the graph of f at x equals c. Okay, So this is the definition of the tangent line of to the graph of f. Okay, and so this limit right here gives you the slope of the tangent line that passes through the point CFC. Okay, so this isn't quite the derivative yet. This is basically a solution to the tangent line problem. But in a second, we'll see how this is very closely connected to the derivative. So let's take a look at a few examples. Let's just ground ourselves in a few examples here. So let's say I want to find the slope of the graph of f of x equals 2x minus 3 at the point 2, 1. Okay, so straight line function, and I just am asked to find the slope of the thing at 2, 1. Now, of course, this is a straight line, so I can just find the slope the old-fashioned way, but let's use this definition that we just came up with and confirm that we get the right answer. So let's let c equal 2, okay? And let's just kind of plug in to this formulation here, okay? So we've got the limit as delta x goes to 0 of f of c plus delta x minus f of c divided by delta x. Okay, now let's plug in the actual function. Well, so first we'll plug in the 2 for c. So f of 2 plus delta x minus f of 2, all divided by delta x. And now let's plug in the functions. All right, so here's where your experience with the difference quotients might benefit you. But basically, you're plugging in f here. This is the function f, but the argument is changed to be 2 plus delta x instead of just 2, okay? And so when we do that, we get this piece here. So I've got f of 2 plus delta x minus 3, okay? And that's this part, okay? And then minus f of 2, right? And that's going to be this part, minus f of 2. So that's just 2x minus 3, and the x happens to be a 2 here. All right, so there's your x. All right, so I get this thing. Okay, so far so good. Let's simplify that. I do some simplifying. And I get 4 plus 2 delta x minus 3 minus 4 plus 3, etc. When I simplify all that down, I get this thing. So the limit as delta x goes to 0 of 2 times delta x over delta x. Okay. Now, you may have already kind of noticed this, but when delta x is going to 0, it's awfully inconvenient that delta x happens to be in the denominator. And in fact, that's how it is in the actual definition too, right? It's in the denominator by definition, so this is problematic. But what turns out to be the case is that in the difference quotient, these delta x's very often cancel. And so that's what you see here, right? You see the limit as delta x goes to 0 of 2 times delta x divided by delta x. Of course, these cancel, and I just get this limit of a constant function, right? So the limit as delta x goes to 0 of 2 is just 2. Okay, so what this is telling me, according to the definition from the previous section, is that the slope at 2, 1 is 2. Okay, is that true? Yeah, of course it is. We look back up here at the function. I can see that this, if I think of this as y equals mx plus b, then I know that the slope is 2 of the whole line. So of course the slope is 2 at this particular point on the line. Right? So we already knew that. But we've confirmed that the definition works in the case of a straight line. Let's try it with a harder function, one that we don't already know the answer to. Okay, so let's find the slope of the tangent lines for f of x equals x squared plus 1 at the points 0, 1 and negative 1, 2. Okay, so now I've got 2 points. But let's not worry about the points yet. Let's just think about this function. Now, if you were to do this without what we just discussed, this would be very difficult to figure out. Like, how would you do this? Like, there's no way to just crank out the slope of a tangent line for a function that's curved like this, right? So this kind of shows you that the tangent line problem is basically solved using this definition, right? But let's go ahead and plug this in. Now, instead of plugging in a specific c like 0 or negative 1, I'm just going to leave the thing as c. I'm just going to leave c in the expression. We'll see when we get to the end. Okay, so I start with the definition. The limit as delta x goes to 0 of f of c plus delta x minus f of c divided by delta x. Okay, and now I'm going to plug in the functions f here, right? And so first I get c plus delta x squared plus 1, right? Remember the function is x squared plus 1. So I plug in c plus delta x for x, and I get this one. Okay, and then minus c squared plus 1, okay, all divided by delta x. Okay, now what I need to do is I need to expand and simplify, right? So this top, I can kind of FOIL this out, and then I can distribute the negative there and sort of simplify this whole thing. And I put a couple steps in just so you can see the steps if you're working through this, right? And so when you do the foiling and you do the distributing, you get this c squared plus 2c delta x plus delta x squared plus 1 minus c squared minus 1 all over delta x. And this all simplifies down. Obviously, you got the c squareds will cancel, the 1s will cancel, and you're kind of left with just basically this piece here, right, which is what you see over here. So the limit as delta x goes to 0 of 2c times delta x plus delta x squared all over delta x. Okay. Now something that's real common to these kinds of problems is you'll see that you have delta x in all of the terms, and so you can factor a delta x out of the top. And so that's what we've got here. And when you do that, of course, you can cancel them. And now you no longer are kind of stuck with that delta x in the bottom. All right, so then you get to this, it's all simplified down, and all we do next is we just let delta x go to 0. Right, and so when we do that, this term goes to 0 and becomes meaningless, and what you're left with is 2c. Right, so in this case, because we left c in the expression, we didn't plug in a specific value of x like we did in the previous example. Now it looks like I have basically an equation. Right, so by working out the problem for a general c, we can now identify the slope of any tangent line for this function. Okay, so that's kind of something there, isn't it? So we can identify the slope of any tangent line for this function by using this formula. The slope is equal to 2 times whatever c is. Now remember, c is the x value, the value you're going to plug into the function. And so this would seem to indicate that the slope of the function is equal to 2 times whatever x value I'm at. So let's take a look here. So the first point we were asked to look at is, scroll back up here, 0, 1, right? So the x value being 0. And the second point we were asked to look at was -1, 2, so the x value being -1. And so let's do that. We can do that down here. So we'll just denote it like this, m sub 0. And so I just take that and I plug it into this expression. So that's 2 times 0 equals 0. So this is telling me that the slope at the point where the x coordinate is 0 is 0. So the slope must be 0. The second one we're asked to plug in is -1. And so when I do that, I get 2 times -1 equals -2. Okay. And so let's take a look at the function. This is approximately what the function looks like, right? It's a quadratic, x squared plus 1. And when we look at the slope of the function at x equals 0, of course we're at the bottom of the graph here. And so the tangent line is horizontal there. And indeed, that's what the function tells us. Okay. When I look at -1, that's over here, right? And so you can think of it as like this point. And the function is telling us that the slope is -2, right? And that looks real reasonable, right? Looks real reasonable because we would be on this side of the parabola, and the slope does indeed look like it would be roughly -2 there, right? And you could graph this with a little more precision, and you could check the rise and you could check the run of a tangent line like this. Okay, and so What's really the key to the derivative is to take this previous idea and extend it a little bit. We can think of m equals 2c, this little equation that we got out of the previous example. We can think of this as a new function that tells us the slope of the original function for any x in the domain of f. Okay, any x in the domain of f, right? I just plugged in two values here, but I could plug in this value, I could plug in that value, I could plug in any value, infinitely many. I could plug them in to this expression here, and it would tell me the slope of my original function at those points. That's pretty powerful. Not only is that a solution to the tangent line problem, that is a whole new thing, right? It is a whole new function that tells me not merely the slope of a tangent line, or not merely what the tangent line is. It tells me the slope of all the tangent lines of the original function. That's a whole new thing, and that is what we call the derivative. So let's take a look at the definition of the derivative. Okay. So the derivative of a function f at x is the function given by this guy here, right? It looks real familiar, and it indeed is the same thing as what we saw in the previous definition, although now we're calling it a function, and we're leaving x as a variable, right? X is no longer a fixed constant. It is a variable, right? And so this is called the derivative, this thing here, provided that the limit exists, and it doesn't always exist. Sometimes for certain functions, the derivative won't be there, or the derivative is undefined at certain points, etc. Right? So we'll get into that in a moment, but this is the idea of the derivative. Okay. And so the derivative is a new function that is derived from the original function and gives you specific information about the first function. Namely, it tells you the slope of the original function for all values of x in the original function's domain. Huge, hugely powerful. Now I can identify the instantaneous rate of change of any function, that so long as I can differentiate it, right? Craziest function you can imagine. I can tell you the slope at any point, so long as I can differentiate it. Extremely powerful, brand new, not an algebra topic. This is the essence of Calculus 1 right here. Okay, so let's talk a little bit more about this new function. Let's kind of go through a few little ideas, a little properties, principles, some notation, and then we'll do some more examples. So the process of finding the derivative of a function is called differentiation, right? And a function is called differentiable at x if the derivative of the function exists at x. Namely, if I can calculate this thing here at a specified x, then I say the function is differentiable at that value of x. And then, of course, just like with continuity and some of the other definitions we've seen so far, we say that the function is differentiable on an open interval if it's differentiable for all of the values in the interval. Okay, so if I can differentiate a certain function on all real numbers, then the function is differentiable on all real numbers, right? For example, right? Or some subset of the real numbers even. Okay, let's talk notation. Okay, we saw this thing here. This is one way to notate the derivative function, this f with a little, like a little dash or a prime, they call it. But there are different ways to notate this thing. And so let's take a look at some of them. And we'll use them all in the course of Calc 1. They all have their place. Sometimes one is more convenient and intuitive than another. I recommend that you just kind of use all of them. Most of them, I would say, actually. But you'll see them all throughout. Like if you're taking a Calc 1 class, you will see these in all of the homework problems. And so let's talk them through. The first one is the one that we already introduced, which is just the name of the function f, and instead of just being f of x, it's f prime of x. Okay, so it's just got this little apostrophe up here. Now, sometimes you'll see y prime, right? So if I specifically have a function like y equals 2x plus 1, you might see the derivative denoted as y prime equals 2 or something like that, right? So y prime, it's kind of similar to the f prime notation, except, it just plays into the idea that sometimes you're not going to use function notation. Sometimes you're going to use y equals 2x plus 1 style notation. And this just works with that case. Now, this other notation is super useful in other ways, and it'll come up a lot throughout the class as well. I'll start with this one, dy dx, right? And this is kind of based on the idea of delta y over delta x, right? But instead of delta, we use this d, right? And as soon as you become sort of infinitely close to the point, or you kind of take the limit, then you get dy's instead of delta y's. And we'll talk about that again later on in the class as well. But this is a nice notation to use. It's algebraically extremely convenient very often, right? And so this notation will be used. And then sometimes when we're just calculating derivatives of functions, you'll see this notation. And so if you think about like dy dx, oftentimes, as you know, in algebra, y will be used to denote a function. And so you can think of this as d dx of a function named y, right? And then sometimes instead of y, we use the f of x, so d dy of f of x. That's kind of the convention there, right? And so this is again, this may seem overly complicated. Why wouldn't I just use y prime? But depending on the circumstances, depending on the context, this could be more convenient, actually. Okay, so this is very nice. Notation is not arbitrary. It is extremely, extremely useful, as we'll see later. Okay, and so as we go through some examples in the rest of the section, I'll try to vary my notation up just to kind of help you see the context of how they're used. So let's take a look at this example. So this is saying find dy dx if you have y equals x cubed plus 2x, right? So find the derivative of y with respect to x. That's what this notation tells you. Derivative of y with respect to the variable x, okay, dy dx. And so I'm being very heavy on the notation in this example. I just want to make sure that kind of see how these things flow together. Dy dx, that's equal to d dx of the y function, which is equal to d dx of x cubed plus 2x, okay, no problem. And so the definition of the derivative is 2 pages up, right? But it's just the limit as delta x goes to 0 of f of x plus delta x minus f of x, all divided by delta x. Okay, so here's my function. I got to plug it in here. Okay, so I get this thing. The limit as delta x goes to 0 of, right, this is x plus delta x quantity cubed plus 2 times x plus delta x, okay, and then minus f of x, all divided by delta x, no problem. Now, this one is kind of a beast because this is a cubed term here, so we got to expand it all to, to get the simplification done. But we can do that. You get x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2x plus 2 delta x, right? So that's just this part. Okay, and then over here, it's going to be minus x cubed plus 2x, right? And then we can simplify it down further. A lot of this stuff will cancel, right? So you can see that the x cubed, for example, is going to cancel, and the 2x's are going to cancel, right? And other things as well. And so then I get 3x squared delta x plus 3x delta x squared plus delta x cubed plus delta x times 2, right? And I got a delta x in every term, so I can factor it out here, right? Once I factor it out, these will cancel. And so I'm left with this thing. Okay. And so at this point, I don't have a problem with the delta x in the denominator, so I can take the limit at this point. So this whole term will go to 0, and this term will go to 0. And what I'm left with is this guy and the plus 2. And so at the limit, this is going to be equal to 3x squared plus 2. Okay, so that is dy dx for this function. That's the derivative of this cubic function. It's 3x squared plus 2. Okay, so remember what this is. This is our derivative, right? So this means this is a new function which tells me the slope of the original function at whatever x value I plug in, right? So if I want to know, for example, what is the slope of y equals x cubed plus 2x at x equals 0, x equals 100, and x equals 1000? Well, I can use this right here. So I plug those values in. The slope at 0 is 3 times 0 squared plus 2, so it's just 2. The slope at 100 is 3 times 100 squared plus 2, so it's 30,002. Right? And I can even plug in the slope. I can even identify the slope at 1,000, so just plug in 1,000. 3 times 1,000 squared plus 2, and so I get 3,000,002. That's the slope. This thing gets pretty steep. Okay, and so this just shows you the power of this. I can find the slope at basically any point that I like. Okay, so that is our introduction to derivatives, part A. So what we're going to do is we're going to pause here and go to part B, and we'll work some more examples and get into more detail about how this thing works. Okay, so we'll see you then.